Okay, so example number 2, we've got a turbine rotor revolving at 3,000 revolutions per minute. So that's giving us the frequency. It's brought to rest, so it stopped, with a uniform acceleration, or deceleration rather, of 10 radians per second squared. So if that's a deceleration, what can we say about this 10 radians per second squared that's not pointed out? It's negative, right, good. Okay, so we've got to find the time taken for the rotor to stop revolving, and then the number of revolutions it's making while it does that. So write down what you know, put it in the appropriate units, and then we'll think about how we're going to do it. Okay, so we know omega 1 is 2 pi times the frequency. Again, the frequency is 3,000 over 60, so that gives us 100 pi radians per second. I should recommend leaving it in terms of pi to start off with. Alpha, of course, is 10, but it's a negative 10 radians per second squared. That's important to realize. And omega 2 is 0 because it's coming to rest. So now we've got to find the time for the rotor to stop revolving. So which formula are we going to use, and then rearrange it to find t. So we're going to use alpha equals omega 2 minus omega 1 over t. What we have to do now is rearrange this for t. So what would that be? Correct. Multiply both sides by t brings the t up on the left, and then divide by both sides by alpha means we get omega 2 minus omega 1 over alpha equals t. So now we've just got to put in the values, and we can work out the time it's going to take for this thing to stop, which is omega 2, which is 0, minus omega 1, which is 100 pi, over alpha, which is minus 10. And that's going to give us minus 100 pi over minus 10, which is, luckily for us, positive 10 pi seconds. Again, we could leave it in terms of pi, or we could then work out what that is. So what would that be? Well, near enough 31.4 seconds. So 3 significant figures. Note that we end up with a positive value for time, which you will do, won't you? We're not going to have negative times unless we're starting at our start point is going to be set somewhere halfway through the cycle or something, so going back in time, it's generally going to be positive, and so that's important that you see how the signs help you to do that. The fact that that's negative deceleration means that this comes out to be positive, which is what we want. Okay. So for part B, number of revolutions, remember one revolution in terms of radians is what? 2 pi. So how do we calculate the number of turns it's going to do? What do we do? So remembering that one revolution is 2 pi radians, to do this, find theta, which is the total angle, remember, the total displacement, the total angular displacement, and then divide this total angular displacement and divide this by 2 pi. Okay, that's what you do in situations like that. If I'm interested in the number of turns it's going to go through, I've got to find the total angular displacement, theta, and then divide that by 2 pi. It will give me the number of revolutions. So that's what you've got to do in this situation. Carry on and see if you can work out the final answer. Find theta, and then divide that answer by 2 pi. So the formula we're going to use to do this is this one, theta equals omega 1 plus omega 2 over 2 times t. We've calculated t, so we actually using something we calculated earlier to do this. We'll look in a second about how we might do that without having to do that. Putting the values in and leaving it in terms of pi. You don't have to do this, but by leaving it in terms of pi, I get theta to be 500 pi squared, because when I multiply this 50 pi in here, which is what this turns out to be, 100 pi over 2, times by 10 pi, I get 500 pi squared. Now when I work out the number of turns, I'm dividing by 2 pi, so one of the pi's cancels out, and therefore 250 pi. And that way you're holding the accuracy all the way through. So finally at the end you can round to the accuracy you want. So there are some advantages to leaving your answer in terms of pi, although it's not required. You don't have to do that. Or we could use this formula. Theta equals omega 1t plus a half alpha t squared. And we put it in, we get exactly the same answer for theta. But there's another way we can do it, because remember, in both these ways, we're using the time, which is something that we've calculated previously. Is there a way to do this problem without resource to that time that we calculated? If we look back to our notes on angular motion, we've got one of the equations of motion that does not involve time, this one. So see if you can work out what theta is without having to use a value for t that you calculated earlier, and you should get the same answer for theta. So just have a go at that now. So we use omega 2 squared equals omega 1 squared plus 2 alpha theta, because that does not involve time. Now we have to rearrange this for theta and then put in the values. So I'll pause while you have a go. So rearranging the formula gives us this. Theta equals omega 2 squared minus omega 1 squared over 2 alpha. Now put in the figures and see if you get the same answer for theta that we had before, which you should do. So we get the same answer, 500 pi squared. There's the numbers put in. This method does not require us to know t. So if we go back to the original problem here, we could have found the angle it turns through in radians. Oh, sorry, that's the wrong example, isn't it? It's example 2. Oh, no. It was that first. It was this one, wasn't it? Yeah. We could have found the number of revolutions made while coming to less without having to find the time. So we could have done B before A. If we're not interested in the time, we could have gone straight to finding the number of revolutions by using the appropriate formula. And which one, how do we find the appropriate formula? We look for the one that involves what we want to find, which is theta, because that's what we need to find the number of revolutions, but doesn't involve time. And so that's when you look back at these original equations of motion for angular motion and say, right, which one is it? This one doesn't involve time. So do I know everything else? Yes, I know omega 2, I know omega 1, I know alpha, so I can find theta.